So now I'm going to look at something called bond duration. This is just meant to be a little bit more involved example of taking a derivative. So a price of a bond is given by the following formula. So P is the price of the bond. And if you look at this, it looks a lot like what we talked about on Tuesday for present value. And so basically the way a bond works is, or at least the one that I've written down the formula for, it has a face value. So let's just pretend that's $100. And it has coupon payments, and it's going to make n coupon payments. And so the agreement I'm going to enter into with somebody is I sell them the bond, so they end up with a piece of paper, I end up with $100. And then every year, so this is sort of set up for yearly coupon payments, I'm going, let's see, I have the $100, they have the bond. I'm going to pay them the coupon payment. So that might be, say, $5. So I'm borrowing their money, and the price of doing that is I have to give them $5 every year. And after n payments, I have to give them $5 plus their money back. So they get their $100 back. So all I'm doing to calculate the price of my bond, so I'm taking the face value, and I'm discounting that n periods. And then I'm taking this stream of coupon payments, and I'm discounting the first coupon payment for 1 year. I'm discounting the second coupon payment for 2 years. Looks like I might have forgotten some parentheses around this, but it's better on this side. Is it? Yeah. And so it's essentially just, it's the same rules that we had before for doing present value calculations, just applied to this slightly more complicated payment scheme of a bond, which is what we did with the annuity, plus you're going to get the face value of the bond back. So C is a coupon payment. N is the number of periods remaining. F is the face value. And then this value lambda, which is sort of playing the role of the interest rate from our last calculations. For bonds, it's called yield to maturity. So I'm going to make just a small change to that. And instead of calling the coupon payments capital C and having them all be the same, I'm going to say C sub little k. And the only real reason I want to do this is now I can just say that all of the short-term ones, so 1 up to n minus 1, or all of that, sorry, not short-term, but only coupon payments one, those are all going to be the same C. And then the last one is just going to be the coupon plus the face value. And so that's going to give me my present value for whatever payment I'm going to receive in the kth period. So now I can rewrite my bond pretty much using the same formula we had last time, except that instead of having a constant value, so I think I called it A last time, I now have something that can be different every time. But for this particular type of bond, it's going to be the same for n minus 1 periods, and then the last one is just going to be face value plus coupon payment. And then I have to divide them by 1 plus the yield to maturity to the kth power, because I need to discount money that I'm going to receive in the future. And the duration of a bond is a weighted average of the times that these payments are going to be made. So I'm going to define the weights as the present value of the payment received in period k divided by the price, and then I'm going to multiply that by k. And so k is just the index here. It's going from 1 up to n. So this is going to be PV1 divided by P, so that's weight 1 times 1. PV2 divided by P is going to be weight 2, so it'll be weight 2 times 2 plus weight 3 times 3, and so on up to n. And when I sum all of those things up, I'm going to call that D, which is duration. And if you think about this, what are the units of PVK? It's a present value of something, so it's going to be measured in dollars.
Did you say that that's the present value of the payment that's made in period K?
Yeah.
Okay.
And then P is just the sum of all of those.
Okay.
So it's the price of the bond today.
So it's current dollars, right?
Yeah. And so what's going to end up happening here is present value is measured in dollars. The price of the bond is also measured in dollars. So when I do this division, I have something measured in dollars divided by something measured in dollars. So I get a unitless quantity. And K, this is going to be dates. So K actually has some sort of units in time. So the way I've written this down, this is for yearly coupon payments. So K is going to be 1 year, 2 years, 3 years, 4 years. So kind of interestingly, this quantity duration is measured in years. And I guess that will sort of seem a little bit more strange once we see how duration is going to get used in this bond pricing formula. And so then another thing I can do is just take this P out of the denominator here and put it on the left side of the equation. And I'm just doing this because this sum of K times PVK is going to be something that falls out of a calculation later. And I'm going to want to be able to replace that with duration times price. Yep.
So I'm confused why we're weighting payments further into the future more heavily.
The present value of something in the future is going to be less.
Less, yeah.
Yeah.
So is it attempted to undo that to get the price?
I mean, here it's not really clear why someone decided to do this in the first place. I think as we go forward, you're going to see that this sort of pops out as a useful quantity in the equation. So, and so I guess, yeah, next bullet point. So sensitivity is, suppose that this yield to maturity rate changes, what's going to happen to the value of the bond? So I'm asking, so that's a sensitivity. If the rate changes a little and there's a big change in the price, we're going to say that's highly sensitive. And if the rate changes and the price stays pretty much the same, then that's low sensitivity. So the present value of the payment received in period K. So here, CK is the nominal payment. So that's, the $5 or the $105. So in period N, I'm going to get $105. In every other period, I'm going to get $5. And then this number in the bottom is going to be bigger than 1. So the present value of that's going to be getting smaller. And so I can write that as C sub k times 1 plus lambda to the minus k. So I'm basically just taking this out of the denominator and writing it like this. So I've always been doing this when I want to take a derivative, so I'm just setting myself up to use the power rule here. So now if I want to take the derivative of the present value of the kth payment with respect to lambda, well, it should be pretty straightforward with the power rule, the linearity, and then you have to be a bit careful because the chain rule comes into play here too, because I actually have a function of a function. But luckily, the derivative of this inside function is 1. So that's a time where you could forget the chain rule and still get the right answer. Not a very safe habit. So this just becomes minus k times c sub k, my argument here, and then minus k minus 1. So that's just the power rule to take the derivative. And then I can rewrite it like this. So that's sort of just undoing this negative exponent trick. And minus k minus 1 is the same as the quantity k plus 1 times negative 1. So that's why we get a power k plus 1 down here. And now if you look carefully at this, we have c sub k divided by 1 plus lambda to the k. But that was just, where is it? Right here, our definition of PVK. And then I have this plus 1 down here, which gives me 1 extra 1 plus lambda in the denominator. and I have a minus k in the numerator. So I end up with minus k over 1 plus lambda times the present value of the kth payment. And now let's look at the price. So my goal was to figure out what's the sensitivity of the price, not just each payment. So if I want to take the derivative of that with respect to lambda, I'm going to take the derivative. So my definition for the price was just the present value of this future stream of payments. And by my linearity property of derivatives, I can move this derivative inside the sum. So the derivative of a sum is the sum of the derivatives. And we've already computed this. This is what I just did on the last slide, the derivative of the present value of the kth payment divided with respect to lambda. And so I'm just going to plug my formula from the previous slide in here. And I get this guy. And now if you look at that, remember what did we say duration was? Duration was k times pvk summed up. So what I'm going to do is take the negative 1 and the divided by 1 plus lambda out in front of the sum. And then I'm left with just the sum of k times pvk, which is this quantity duration that just sort of falls out of us taking the derivative. And this quantity here, so negative 1 divided by 1 plus lambda times the duration, is called, not the negative, everything but the negative, there, is called modified duration. And so the sensitivity, the rate of change of the price with respect to, you can think of this as the interest rate, is equal to minus the modified duration times the price. Okay, yeah, so dm is modified duration. And so this is what we found now, that the derivative of the price with respect to the yield to maturity is the negative of the modified duration times the price. And I'm going to make one more little substitution here. So since the price is obviously going to be non-zero, I can divide both sides by price. And now I have the change in price with respect to a change in the yield to maturity divided by price. So the change in price, that's going to be something that's measured in dollars. So if a price changes from $100 down to $80, the change in price was negative $20. If I divide that by the price, now I have some sort of rate. So it doesn't matter what the price was. You know, if it went from 100 down to 80, or if it went from 1,000 down to 800, this thing on the left is going to be the same. And so that's going to be our interpretation for the modified duration. So it's going to give us some measure of the relative change in price as the yield to maturity is changing. And kind of in summary, duration then, which is something measured in years, is a measure of interest rate sensitivity. Yes?
Can I think it as a slope, like random rates, so it's sensitivity of will price change the longer change?
Mm-hmm. You mean like that?
Yeah.
Okay.
Yeah, I really question.
Okay. And so essentially all we've done here is we've just figured out what this curve, so this is the curve in the price yield to maturity space, so it's called a price yield curve. And I've calculated the derivative, so that's just going to be the slope of this tangent line. And so then one of the main things you're going to use a derivative for when you can find a tangent line like this is if you look at this, maybe between about 8% and maybe 12 or 13%, this tangent line is very, very close to the actual curve. And it's going to be easy to evaluate points along the tangent line because it's just a linear function. It actually can be quite difficult, especially when people were trying to do these computations before you had computers, to evaluate points along this curve. So one of the ideas of doing this approximation in finding the tangent line is it gives us a good way to make local approximations to our function value. And you can actually improve this. So what we've done here is just a first order approximation. We're trying to approximate this function with a linear function, so a tangent line. You can also use convexity, which is sort of how quickly the second derivative, so the size of the second derivative, it's sort of how quickly this curve is changing slope. And that allows us to make an even better approximation. And we'll come to that in the second half of this course, so after the midterm. Okay. So just quick summary. This is a formula for duration. You can also multiply the price on the left-hand side and get this k times PVK. Modified duration is just 1 divided by 1 plus lambda times duration. And then the price sensitivity formula is, so the rate of change of the price with respect to a change in the interest rate is minus the modified duration times the price.